This video discusses counter-controlled loops, such as the for loop, and also data structure iteration using things like for each loops. In this code, we ask for a number up front and then loop and print the number that many times. So I enter a number, I'll enter 5. The code outputs 0 through 4 before finishing. And the way it does that is by breaking up the loop into 3 and 4 portions if you count the body. So we have an initialization section, which is executed exactly once before entering the loop. A test that is executed before each iteration, if this ever evaluates to false in languages like C# or Java, or evaluates to 0 in languages like C and C++, then we will exit the loop. Otherwise, we first execute the loop body, and then after the loop body, come back and execute this update statement. So this loop runs as long as I is less than x. We print out the value of I and then increment I afterward. The initialization portion of the loop can initialize multiple variables, and the update can also update multiple variables in different ways. So now I'm looping through I and j. I'm going to print j, but the test condition will be based on I. And if I run this code, I provide the number 4, but it prints out 0, 2, 4, and 6 because although we are looping, when I takes on values 0 through 3, we're printing out the values of j. Also note that each portion of this loop is entirely optional. We can remove the initialization and move it before the loop, and we can take these update commands and make them occur at the end of the loop body, although we'll have to separate them with semicolons rather than a comma. This code is currently identical to what we had before. If I run it, it asks for a number, provide 4, it prints 0 to 4, 6. The test is also optional, but if I remove the test, then it always evaluates to true, which means we have an infinite loop. So we will have to have a means of escaping the loop here. The original test was if I is less than x, but we want the opposite of that, so I'll put an exclamation to negate that. And if that opposite is true, we will break. So this code will behave the same. This break command is an example of an extremely limited goto statement. Break causes the code to exit the innermost loop that it occurs inside of. So there's only one loop here, so we exit that and go to or jump outside the loop to this command here. But the use of a break becomes a bit more complicated when it occurs inside of nested loops. In this code, we have an outer loop and an inner loop and a break inside the inner loop. The idea is that we keep asking the user to enter a number, and then when the total exceeds 100, we will break to exit. However, this doesn't quite work the way it is intended. When I run this code, I enter a number, 5, and it tells me the total goes to 1, then 3, then 6, then 10, then 15 as we add numbers to it. I'll enter another number, 20, and we keep adding to that, and I've actually exceeded 100 now, yet I'm still running. What's going on? I'll put in another number, it keeps going, put in yet another number, and it keeps going. Now the reason that only one line of output is appearing here and here is that the inner loop is breaking and exiting, but the outer loop continues. The outer loop has to go 10 iterations before we exit it. That is a flaw in this code, and if I enter enough numbers here, we'll eventually complete 10 iterations of the outer loop and the code will finish. But what we want to do is exit not only the inner loop, but also the outer loop once total exceeds 100. Now, one way we could do this is simply add an additional break here that would solve our problem. I enter a number, I exceeded 100, and then I exited both the inner loop and the outer loop. I'll run this again just to clarify that if I started small, I could in fact execute the loop multiple times and only exit once I finally exceed 100 in the inner loop. This involves some repetition though. One other option would be to change the loop condition here. Loop as long as I is less than 10 and total is less than or equal to 100. This gets the same effect, but once again requires repetition of a check on total, albeit a negated version of that check. Interestingly enough, in the Java programming language, there is another option. Java added support for what are called labeled break statements. This code is very similar to the C++ code we just saw, except we're doing I/O in the Java fashion using a scanner. But the most important difference for the purpose of our discussion is that when I break to the label outer loop. The label outer loop occurs here, followed by a colon. When I run this code, I'm asked to enter a number. I enter some small numbers at first. The value of total gradually accumulates. Then I enter a large number. The final total reaches 107, and it breaks out of the inner loop all the way to the outer loop label without the need for any additional break statement or condition on the outer for loop. The C-based languages, including Java, also have support for another restricted form of goto known as continue. Continue can occur inside of a loop, and whenever you see it, what it does is it skips the rest of the current loop body, performs the update in that loop, and starts the next iteration. So it's a way of continuing the loop, but not executing the code or the remaining code of the current iteration. So in this code, I'm looping from 0 to 5. I get a value of input, and if that value is negative or 0, I skip it and go to the next iteration. Otherwise, I loop 5 times in the inner loop and add to total that number of times. So when I run this code, a value of 2 accumulates values in total, adds as a value of 3. But if I enter 0, nothing happens. I enter negative 2, nothing happens. Because in each of those cases, this if statement caught that negative input or 0 input, skipped this loop, but still increased the value of I to start the next iteration. And if at this point I enter another positive value, it will add values to total, and that creates 5 iterations of the outer loop, which is why we now exit that loop. The flexibility of the C-style for loop is very powerful, which is why it is persisted in a number of languages. Being able to optionally have or not have these 3 different components of the loop, including the variety of restricted goto statements, makes this loop capable of doing almost anything a programmer would want to do. However, it does make analyzing and troubleshooting some programs quite difficult, which is why other languages have opted for more restrictive for loops. One of the most famously restrictive languages is Ada, which puts safety and reliability above all else. This is an example of a basic Ada for loop, where we specify the loop variable and say that it must be in the range 1 up to 10 for an integer type loop variable. And then on every iteration, we print that integer and we end the loop specifying the label for the loop that we are terminating. The output of this code is here. Note that despite the restrictive for loop form, Ada does support raw gotos. In this example, once I is greater than 6, we go to the label outside, specified here using sharp brackets on both sides. When I run this version of the code, the output stops at 7, because once 7 is output, we check to find that 7 is greater than 6, and then execute the goTo command. However, a more targeted way of doing this without using a goTo is to use Ada's exit statement. This specifies that I exit the loop named for loop when I is greater than 6. Executing this provides the exact same output as our previous code using the goTo just did. This construct is roughly equivalent to the break command in the C-based languages, but is as flexible as the version in Java that allows you to break to a specific point in the code. Python's for loop is also interesting because it is actually a for each loop. If I say for I in range 6 print I, that code will print out the values 0 through 5, stopping just short of 6. This range command is actually a function that returns a list. I can modify it with an optional stopping point, going now instead from 6 to 10, but excluding the 10. And I can even change the size of the step. With a third parameter of 2, I start at 6, jump 2 to the 8, and then jump 2 more to the 10, but this loop goes as long as I am strictly less than 10. However, this is not actually interesting loop syntax. All the Python loop is doing is looping through the contents of the list returned by this call to range. Note that a range object is a special type of object in Python, so if I want to see the structure of what's being returned here, I have to actually convert it to a list. And so this list contains 6 and 8, and those are exactly the values that are printed out if I loop through it using the for loop. In fact, I could insert an arbitrary list here, and if I loop through that, Python will print those values. In general, this is the approach that Python uses for its data structures. The for loop loops through whatever that structure is, assigning each value to the loop variable accordingly. Support for each loops has also been added to Java. In this example, a Java array list has 3 values added to it, and then we have a for each loop. The Java for each loop uses the same for keyword as the regular loop, but inside the parentheses, we have first the value that will be assigned a new value on each iteration, then a colon, and then the data structure being iterated over. When I run this code, it prints out the contents added to that list. However, in Java, the use of a for each loop is actually merely a disguised use of a special class known as an iterator. Here is equivalent code using an iterator class. Here, the for each loop has been replaced with a while loop, but this is fine because the iterator class, which is directly derived by calling the data structure's iterator method, is used instead. On each iteration, we first check if the iterator has the next element, and if it does, we get that next element and print it using the println statement. And the output is the same as the for each loop. The reason for these many features is to aid in expressivity and writability. Programmers want to be able to do a lot with very few statements. So although it is possible to represent all flowcharts using merely a while loop and an if statement, one can often write much more elegant code using one of the many constructs discussed in this video instead.